So we are looking at right, looking at multi-arm bandit problems. Right. So we looked at a couple of ways of solving it. So essentially you try to keep an estimate of the value function around, right. The value function is the expected payoff that you get for pulling an arm, right. You keep an estimate of the value function around, and then you behave some exploratory fashion with respect to that value function that you have, right. So either you do epsilon greedy or you do softmax or something, and you get some kind of asymptotic guarantees, correct? Yes, okay, good. We also spoke about other forms of optimality. So one of them we spoke about was regret optimality. So regret optimality is what? Reducing the total, I mean, or increasing the total reward that you get over the process of learning, right. So the initial loss that you get due to the exploration you want to minimize, so that I come as close as possible to the optimal case as quickly as possible, right. So that is essentially what regret is all about. And so we will start by looking at one algorithm which in some sense has become the most popular bandit algorithm around right now, because it is so easy to implement and also gives you not too bad regret bounds, okay. It is called the upper confidence bound. The upper confidence bound algorithm or the UCB algorithm, okay. So I will use slightly different notation today, right, not too different. I will try to, as much as possible, I will try to translate on the fly, okay, to the notation that is used in the textbook, right. So even though we will be giving you some papers to read, you can take care of linking the UCB paper and the median elimination paper and other things, right, on Moodle. We will be giving you some papers to read, and the notation in the papers will be very different, okay. You probably have to spend like half an hour just trying to understand the notation, but when I am explaining it in class, to the extent possible I will try to map it to the notations used in the book, right. So that you have one uniform set of things that you can keep track of throughout, right. The changes are the following, right. I am going to assume that there are capital K arms, right. So earlier I was assuming there were n arms, but it turns out the reason I want to change n is we are going to now talk about a notion of time, right. So there are going to be pulls at every time instant and so on and so forth, and this should be familiar to electrical engineers. So if time is discrete, you denote it by n, okay. If time is continuous, you denote it by t, right. So I want to be able to denote discrete time, so I want to use n for discrete time, okay, and so we will save n for discrete time and I will not use that for the number of arms. So that is the reason I switch to k, okay. Assume there are k arms, and so as before with each arm there is associated some arbitrary probability distribution which I do not know, right. Whenever I pull an arm I will get a sample drawn from that probability distribution. It could be Bernoulli, it could be Gaussian, right, it could be Poisson, we do not know what distribution it is, but according to that distribution we will get a payoff, right. And what else did we assume last time? That there is the expectation given for that distribution, right. We assume that the distribution is stationary, it is not going to change with time, right, and that there is an expectation associated with that distribution which we will denote by q star of A, right. When you say q star of A, it is the expectation for pulling arm A, okay, that is clear. Right, so here is the UCB algorithm. So let us assume there are k arms. So the initialization phase is play each arm at least once, right, play each arm once, right. You have to pull every arm at least one time, you can't do better than that, agreed, right. If I never pull the arm, I do not know anything about that arms, right. So I need to pull each arm at least once, so that is the least. So we start off with that and then we do the following in a loop. So remember what Qj is the estimated payoff, the expected payoff, right. So this is average reward that we will be maintaining, right, that is a value function, right, for arm j. So Qj is the estimate that I have at time n, right. Qj is the estimate I have at time n for arm j. So essentially what I am doing is I am taking whatever is the current estimate, right, and I am adding this expression to that, right, and then I am playing the arm that gives me the highest value for this total expression, right. So the way to think about this is the following. I will come back to this, we will show things more precisely later, but let us assume that this is my Q of arm 1, right, whatever is some scale. This the x axis, the x axis let us assume is the arm index and the y axis is the expected payoff, right. So that is Q1, then I have Q2, say Q3 and Q4. Let us say I have 4 arms, right. So what the idea behind upper confidence bound is to say that, hey, I am not going to use just the estimated expectations so far, right. So I have actually drawn many samples, right. I can use the samples that I have drawn so far to figure out what is the confidence with which I can say that this is the expectation, right. So you can think of giving some kind of a bound around this. You can say that, okay, this is the expectation I have, right, but the true value of Q1 or Q star 1, right, the true value of Q star 1 is going to lie within that band, right. So intuitively you can see that the more number of times I have sampled arm 1, the smaller is this going to be, right. If I have taken a lot of samples, then I am more confident about the expectation that I am going to tell you, right. We know that as the number of samples tends to infinity, this Q will converge to Q star. So we know that, right, Q1 will converge to Q star 1 if the number of times I have sampled 1 goes to infinity. So the more the number of samples I draw, the narrower will be this band of uncertainty, right. So likewise I will have a band like this for Q2, right, I will have a band like this for Q3, I will have a band like this for Q4. So what arm am I suggesting that you take now? No, I am saying take arm 1, that is what essentially UCB tells you, right. So why do you think this kind of a scenario might have happened? I might have chosen arm 4 a lot of times because it seems to have a higher value. So my uncertainty and the value of arm 4 has come down a lot, right. But arm 1 I have not taken enough times, arm 3 obviously I have not taken enough times, but I am really not inclined to take arm 3 anymore, because given my current state of uncertainty, right, the probability that arm 3 will be higher than this end, right, I mean it is very small, right. Even though my uncertainty arm 3 is very high, I am not inclined to take that arm because the chance that it will truly be high the chance that it will truly be high is very small, right, while for arm 1 the chance that it might be better than arm 4 is fairly decent. So this interval I am telling you is some kind of bound that says that with very high probability, right, the true value of Q1 will lie within this bound, right. That means there is a chance that it will lie here, which case it can be higher than Q4, right. So, I will take this. If I take this a few more times and let us say after some time my estimate moves up like this, but my estimate moves up a little bit, but my bounds also shrink, right. Now it might not look attractive compared to Q4, so I will go back to taking Q4, right. So, that is why you can see in this expression I have the total number of samples I have drawn of arm j, right. What nj is the number of times I have sampled arm j. So, the larger the nj, the smaller this expression is going to become. Okay, so, larger the number of samples I draw, the smaller this expression will become, and therefore, this interval will keep coming down. Okay. What is that? Yeah, that is more like a normalizing term, right. It is there in all the expressions, all the values, right, all the intervals that you compute. So, it is not relatively, it is not going to matter, but you will need it to show some results later. So, so the algorithm itself very clear, right. So, the things here, the n is essentially the number of times I have played arms so far, any arm, nj is the number of times I have played arm j. Okay. So, you have that pictorial description of what this algorithm is doing, great. So, what is nice about this algorithm, it is a very simple algorithm, you saw that, right, there is nothing about it. All you need to do is, apart from keeping track of qj, you have to keep track of nj as well, which you are anyway doing if you are doing that incremental update, right. If you remember in last class we wrote the incremental update. So, the step size was anyway related to nj. So, the only additional overhead would be if you had been using a constant alpha for your updates, you will have to remember nj in addition, otherwise it is exactly the same thing like we did for epsilon greedy. So, instead of randomly deciding which action to take for exploration, you do not do any exploration also, the random number generator also is gone now, right. This is a very deterministic algorithm, right. So, what is so great about it? Yeah.
So, don't we need some kind of normalizing on qj?
No.
Because the other term might be a very small term even when q might be a very large value.
Does not matter. Why does it matter?
Like qj, like the expected payoffs can be something like 10.
That way. Okay, fine. Yeah. So, all of this particular form of expression does assume that the rewards are bounded between 0 and 1.
Okay.
Right. So, yeah, I will come to that in a minute. So, yeah, you are right. So, essentially you can rescale the rewards if you want to, right, as long as all the rewards are positive. So, you can rescale them to lie between 0 and 1, but if you have negative rewards you will have to think about how you want to do this. Okay.